Good morning, Chem 103. I hope everybody's doing okay. It was great to see half of you yesterday in lab. So today we're going to talk about ions and ionic compounds. Please make sure if you haven't watched the video from last week on macronutrients, please do that. That'll give you some context from lab this week as well. This is not really related to that, but it is another important aspect of chemistry and of some of the things that we're going to see in the future. Okay, so let's get started with this. Well, up until this point, when we talked about chemical bonding and chemical structures, we were looking at covalent compounds. That is, where we have two atoms sharing electrons and we build up these big organic molecules from them. That's been exclusively what we've looked at in terms of chemicals this semester so far. But there's a whole other class of chemicals, the ionic compounds, that bond in a different way through ionic interactions. Now, we talked about ions back at the beginning when we looked at the structures of atoms and how many electrons and protons and neutrons, and that kind of stuff. So this is kind of extending from there, and now we're going to look at what happens when those ions come together to form compounds. So let's start with just reminding ourselves about what ions are and where they come from. If we have a sodium atom that we might write like that, then we can look at sodium on the periodic table, right over there, and you can see that it is element number 11, atomic number 11, which means it has 11 protons. 11 protons. We know we can't quite count the neutrons this way because we haven't given an atomic mass. We're not going to worry about that for now. But electrons, we can also know, because if it's a neutral atom, that means that it has to have an equal number of protons, which are positively charged, and electrons, which are negatively charged. So 11 protons, 11 electrons, and it's neutral, has zero charge. Well, one thing that sodium can do is it can lose an electron to become sodium +1. And I know we did this before, but just to kind of refresh everybody's memory, we now have 11 protons and 10 electrons, and so there's an extra free electron, which is expressed sometimes as E or E minus, and that's just sort of floating around there. So it's not floating around, it's somewhere else, but it's left the sodium atom. So now sodium is no longer neutral, and this is now what we call a sodium ion. So let's just label those. This is a neutral sodium atom with zero, no charge. And this is a sodium ion with a +1 charge. All right, well, other atoms form negatively charged ions. We've seen some of these as well. Let's look at oxygen, for example. Now, oxygen we're going to write a little bit differently because it doesn't just exist as a single O atom. It exists as an O2 molecule. And that is oxygen. We might call it molecular or elemental oxygen. And it also has zero charge here. And oxygen can gain electrons to become O2 minus. And this we have to do a little bit of balancing here to make sure, make sure we have enough electrons and everything. Don't worry about that too much just yet. We'll talk about chemical reactions a little bit later. But here we have oxygen, neutral elemental oxygen here, and then this ion that's formed over here is called oxide. So this one actually has changed its name on becoming an ion. And that's common for negatively charged and positively charged ions. Positively charged ions tend not to change their name, so sodium, sodium, whereas negatively charged ions tend to change their name, so oxygen becomes oxide. And usually it's "ide" that is this suffix that changes. Okay. So let's look at now what happens when these ions start combining into ionic compounds. So let's say we have something like we want to make a compound of these two ions that we just talked about, and that compound might be called sodium oxide. You have sodium, you have oxide, you put them together, you have sodium oxide. Now, what does that actually look like? Is it kind of like what we were talking about before, where we, what we've seen before, where we draw a line in between? Well, it turns out it's not. What's happening with ions is because they're relatively stable as they don't tend to form these types of covalent interactions where they're um, sharing electrons the way that other compounds do. So we don't use those lines to express the bonds because those lines mean something very specific. They mean two shared electrons. Instead, what happens in ionic compounds is that they simply attract each other because positive and negative attract. So in a sodium oxide compound, you'd have some sodium ions, you'd have some oxide ions, they're bigger, and they just sort of hang around each other. And if they're a solid, they form a packed lattice. So you can imagine all these spheres packed in together. And it just kind of goes on and on. And so on. So that's what an ionic compound might look like, just positive and negative ions interspersed interacting together. When a compound like sodium oxide is dissolved in, let's say, water, then, although I don't think sodium oxide is soluble in water, but something comparable dissolved in water, the net positive and the negative ions split apart and get surrounded by water molecules in solution. All right, so how do we express a compound like sodium oxide as a formula? Because it has, essentially infinite sodiums and oxides all connected together, billions and trillions, whatever of them. So how do we express that as a compound when it's not just, or as a formula when it's not just a discrete molecule? And what we do is we come up with a formula that allows us to balance the charges of the two ions. So if we have sodium +1 and we have oxide -2, we can't just smush those together and say, okay, the formula is NaO. Because Na and O as ions don't balance each other out. We would have +1 and -2. That doesn't equal 0. So we want to put the compound together in such a way that ends up with an overall 0 or neutral charge. So to do that, we're going to add another sodium. And we're going to say that this is the ratio that these things exist in a compound. We're always going to have 2 sodiums for every 1 oxide. And that way we can have +2 overall and -2 overall. And so that's going to be neutral. And then the way we express all that in a formula is using subscripts, just as we did with the molecules. So this is going to look like Na2O, and that's what an ionic compound formula will look like. All right. So our goal now, and my goal for you in this part of this class, is to be able to write chemical formulas for ionic compounds from their names. Okay, so that's what we're going to try to do here, and I'm going to show you how to do that. It takes a little bit of work sometimes, and notice we're not going the other direction. So I'm not going to ask you to name the compounds from their formulas. That's a little bit trickier. It's a different set of rules. So we're going to focus on writing chemical formulas from ionic compounds from their names, for ionic compounds from their names. So a couple things we have to know to be able to do this. So let's say we have some name of a compound. Magnesium chloride. So first, how do we know it's an ionic compound? Well, we know it's an ionic compound because it's made of two ions, a metal and a nonmetal. And for our purposes in this class, if we ever see stuff from the metal part of the periodic table combined with stuff from the nonmetal part of the periodic table, we can assume that that's ionic. Now, that's not always going to be true for all of chemistry, but for our purposes, that works okay. All right, so our first step is we need to know the chemical, the symbols for these elements, and we need to know their charges. Once we have those, then we're good, and we just have to put it together. So let's make a little note to ourselves that we need to know or to find out the symbols. That's easy. We just look it up on the periodic table. And the charges, and that can be a little bit more tricky depending on what we're doing. So let's take this step by step here. So first, the symbols. We look up magnesium on the periodic table, and we find that it is right over there, number 12, and its symbol is Mg, so that's not too bad. Chloride is a little bit harder to find because there is no specific chloride on the periodic table. What there is chlorine right here, and that's going to be our chloride because we know now that sometimes the ions can change their name, can change their suffix from whatever it is on the periodic table to "ide" when it becomes an ion. So we're going to say, all right, we know chloride is kind of close to chlorine, so I'm going to assume that's our symbol. Okay. So number one done, we've got our symbols. Okay, now how do we find the charges? Because depending on the charges, we're going to have different ratios here. So we need to know, are they +1, +2, +3, -1, -2? How do we find that out? The answer to that is that the periodic table gives us a clue here as well. There are some segments of the periodic table that always have the same types of charges. And so I'm going to draw a quick periodic table here to show you this. All right. So if this is our general shape of the periodic table, we can split it up into some groups or families or columns. We've got row 1, we've got row 2. And all the atoms in row 1 always make +1 ions. And all the atoms in row 2, column 2, always make +2 ions. So that's really nice because anytime we see one of those, we can automatically know what type of ion we're looking at. There's a couple other spots in the periodic table that make these predictable ions, and then there's a whole bunch in the middle where we can't figure it out that way, and we'll get into that later. So over here, we've got aluminum in row 3, which is +3. Unfortunately, boron just above it and the atoms below it don't quite work out so nicely. But aluminum is important enough that we should remember that it's generally +3. I believe actually that's row 13, not 3. So we're just ignoring all this middle stuff for now. Then coming in from the right side, these atoms, the noble gases in row 18, don't really make ions. So we kind of don't even have to worry about them for this project. In row 17, those are all generally -1. In row 16, they're generally -2. And I'm going to squeeze out 14 here. That's okay. We're not going to worry about it. And then in 15, we're -3. 14 it gets a little bit more complicated, so we're not going to we're just going to ignore that one. So you can see what's happening here is that most of the periodic table in this whole big middle section, we can't find the charges by looking at the periodic table, and that's because those atoms either have more complicated behavior or they just have multiple different possible ions. So we can't say for sure what the charge is going to be. But in these particular spots, we can. So let's look back at the periodic table with all the elements and look at some of the ones we're looking at. So over here on the right, again, we're going to, noble gases up here, we don't really have to worry about. They don't make ions. Then the next column over 17, these are going to be -1, then -2, and then -3. And when we get down into the metalloid area down in here, things start to get a little bit more weird. So we're going to really focus more on these top few elements. So those are the atoms that have predictable charges. So now using all that, going back to our example, if we want to know the charges on magnesium chloride or anything, we're going to first look at the periodic table and see if they lie in those areas that have the predictable charges where we know what the charge is. And magnesium does. It's right here in column 2. So we know that that's going to be a +2 or a 2+ ion. And then chlorine in the periodic table, chloride the ion, chlorine is going to exist in column 17 here. So we know that's going to be a +1, or sorry, a -1. So chloride's going to have -1. And usually when it's just 1, we leave the number out. So we've figured it out. We've got our positive and negative charges. And now all that's left is to put together a compound so that the charge is balanced. And to do that, we need 2 of the -1s to balance the +2. And so our compound looks like MgCl2. Okay, so that's how we find that type of a compound. Let's try another example. Aluminum oxide. So same technique. We're going to look at the periodic table. We're going to find aluminum, which is right there. We're going to find oxide, which is not in the periodic table, but it comes from oxygen, which is right here. So we've got aluminum in 13, and we've got oxygen in 16, and we can find those charges based on what we just did up here. So we've got aluminum, Al. We've got oxygen, O, or oxide, O. And then we look up at this guide, and we say, all right, aluminum we know is going to be +3, and oxide we know is going to be -2. Now, putting these together in a way that balances the charges initially looks like it's not going to work, because if we see aluminum has a higher charge than oxygen, so we think, okay, well, we just need more oxygen. But now, of course, we've got too much oxygen. We've got -4 to +3. So we have to find a common multiple so that we end up with the same charges plus and minus. And that common multiple ends up being 6. So if we have 6+, we can get 6-. And that's just a limitation of the fact that they have to be whole number ratios. We're not having fractional subscripts. So the subscripts have to be whole numbers. So we have to kind of keep adding on both sides or multiplying or however you want to think about it until we can get those whole number ratios. So our formula ends up being Al2O3. So 2 aluminums and 3 oxides in that formula. All right. So now what happens in that middle part of the periodic table? Let's look at that. So let's say we're looking at ionic compounds with iron, which is Fe, or cobalt, or nickel, or platinum, or even over here, things like lead, tin, that don't fit nicely in what we just did. Well, the key to those is that the name is going to look a little bit different. Because those compounds or those elements make different types of ions, we have to specify which ion we're talking about right there in the name. So there was an older way of doing this where you'd have different words for the different charges, like ferric and ferrous, and sometimes you'll still see stuff like that. But the more systematic way to do it, that's easier to use also, is to put the charge on the positive ion in parentheses. So this 3 here, this Roman numeral 3 in parentheses, tells us the charge on iron is +3. So now when we go to write our ions, we know that iron is +3 and chloride is still -1 as it was in the last example. So we get the charge directly from the name in this case. And now all that's left is to do that balancing. And so we've got 3 plus and 3 minus. So our formula is FeCl3. The reason for that is because there is also an iron 2 chloride, FeCl2. And one tricky thing to remember here, not really tricky, but just a common mistake, is that the Roman numeral only gives you the charge on the ion. You still have to do the balancing. Everybody always wants that to mean subscript. Everybody wants it to be like, oh, iron 3 chloride, it must be iron 3 chloride. But that's not how it works, because that number would change depending on the counter ion. So iron 3 is a specific ion, iron plus 3, this thing. And you can't get the subscripts directly from the Roman numeral. You get the charge from the Roman numeral, and then you have to still figure out the other stuff. Okay. And then our last category of being able to being able to meet our goal, that is, write formulas for ionic compounds from their names, is something called polyatomic ions. So these are ions with more than one atom in them. And they're not on the periodic table because they're made of atoms from the periodic table. We've used some in lab so far, so things like nitrate, NO3 -1, hydroxide, OH -1, there's many of these. I'm just going to put in a few of the really common ones. Sulfate, SO4 -2. Phosphate, PO3 -3. And let's also look at carbonate. There are some positively charged ones as well. So NH4 +1 is ammonium. And so good news and bad news with these. The bad news is there's no way of really figuring these out from the periodic table. You just have to know nitrate is NO3 and it has a charge of -1. Hydroxide is OH and it has a charge of -1. But the good news is you, in this class, don't have to memorize these. You can look these up on a table, or a table will be given to you for quizzes, things like that. What you do have to be able to do is recognize that these are not on the periodic table. So if you see a name like sodium phosphate, all right, we recognize sodium as an element. We find it on the periodic table. But phosphate is not on the periodic table. And if you look on the periodic table, what you will see is phosphorus. And so you might think, oh, okay, phosphate, it's P. But it's important to recognize that that's not P. And the way that we know that is from the suffix here. Instead of "ide," it's "ate." So whenever a monoatomic ion exists on the periodic table, like chloride, sulfide, oxide, phosphide, its polyatomic ion is going to have a different suffix like "ate." So we see that and we recognize that this is not on the periodic table. This is not just P. It's something else. And so you have to go look in your polyatomic ion table to see what it is. And so we look it up and we see it's PO4 and its charge is 3 minus. Then we can add our sodium here from the periodic table that we know is +1. And now we build the compound the exact same way. So we need 3 sodiums to balance the -3 phosphate. And so our formula is Na3PO4. We can also use these with other types of ions, such as the ones in the middle of the periodic table. So let's say we're looking at trying to find a formula for cobalt (3) hydroxide. Okay, well, how would we write that? Well, cobalt 3, we know what that means now. That means we look it up on the periodic table, it's CO, and the charge is +3. And then hydroxide we recognize as a polyatomic ion. We look it up on a table of polyatomic ions, and we see here that it is OH and -1. And so to balance this formula, we need 3 of those. So 3 plus, 3 minus. And the way we write this when we want more than one polyatomic ion in a formula is to use parentheses so that it's clear that we mean that we need 3 of the entire unit. Notice in all of these formulas, all the way back, once everything's in a balanced formula, we leave the charges off. So we use the charges to help us out and to kind of get everything worked out. But then when we write the formula, there's no longer charges shown here, because now the subscripts allow us to understand what the charges are on something like cobalt, for example. All right, so this is how you write ionic compounds from their names using a couple different types of ions. So ones that are in the periodic table and clear, like it's clear what the charge is, because they can only have one charge, or ones where it could be some different charges, and then ones that involve polyatomic ions. Notice the polyatomic ion, the techniques of how to put the compound together are the exact same. There's nothing special about using polyatomic ions, except they have their own formula and charge that you have to either know or look up on a table when you're trying to do that. All right, so hopefully that's helpful. And let me know if you have any questions. Otherwise, have a great weekend. Thanks, everybody.